Okay, so we're back and we're going to look at some examples. Most of them will just be equations of functions. This time out, we have something actually graphed, and you can see the question's asking if it's continuous at x equals 2. And you can clearly see that in this graph that's given to you that there is it is discontinuous at x is equal to 2. There is a removable discontinuity. You can see the hole in the graph and the point is elsewhere. So you can see visually that it is definitely discontinuous. So it has failed the continuity test. But we have to actually go through a formal mathematical proof to do this. So let's get started. The first thing is, does f of 2 exist? And the reason I picked 2 is because the question asks at the specific x value of 2. They have to tell you what x value we're looking at. So does f of 2 exist? It definitely does exist. It's a point that's dropped down. It's equal to -1. So it meets the first criteria. Okay, the first condition it passes, f of 2 does exist. The next one is, does the limit as x approaches 2 exist? And the answer to that is yes, it does exist. The answer is 3. You can see the left and right hand limits, and you can include this if you wish, okay? You can say that as x approaches 2 from the right side is equal to the limit as x approaches 2 from the left side, which is equal to 2. Both limits are equal, and that is not a 2, sorry. I'm not erasing this video. Okay, we're just going to continue, mistakes and all. It's actually equal to 3. You can see that the y value here is x approaches positive 2. You can see the y values are approaching 3 from both sides. So the limit does exist. So it meets the second condition. But it does not meet the third condition. The third condition is that the first two conditions, the first two values had to be equal. In this case, they are not. Okay, -1 is not equal to 3. So we fail the third condition, and therefore we make some sort of a statement. We're going to say right here, we're going to say that f of x is discontinuous at x is equal to 2. And we proved it formally by going through the 3-point definition. We had to get until the third condition before we found a condition that failed. So in this case, the function is discontinuous. And you knew that already by looking at the graph, but we have to present a formal proof. So it's not like the proofs that you do in grade 11 with the triangles where you have statements and reasons. Okay, we're doing these in a different way. This is a specific type of proof, and we're going to move on to question 2, where we do not have a graph, and you are not asked to sketch a graph. We're just going to use the function only. Is this function continuous at x is equal to -6? Okay, well, let's take a look. First thing is, we have to see, does f of -6 exist? And the answer to that is no, because if we plug in -6 for x, you can see right here that we are going to come across a situation where we have 0 over 0. That is not a defined answer. Okay, f of -6 does not exist, and it fails the first condition. If it fails the first condition, then it cannot be continuous. There's no reason to continue on to the second and third point. Once you get one x, you can just say x as in the wrong, incorrect, okay, or not meeting the condition. You can say at that point it is not continuous, but you have to make some sort of a statement. You can't just leave your answer like this, okay? You actually have to answer the question. So we're going to say, therefore, f of x is discontinuous at x is equal to -6. Okay, let's take a look at one last example. This time it's a piecewise function, and it's broken apart at -1 for x, or is it broken apart? Let's find out. Okay, so first of all, you could graph this. Okay, that's one way of doing it. It is a long way of doing it. You have to go through table of values and sketch the graph and all that sort of thing. That's a lot of work, but it can be done. But let's present a formal definition. So let's first of all figure out, okay, does f of -1 exist? Okay, it definitely exists, all right? You can see right here that we have to plug in -1 for x into the first function. So what I'm going to do right here is I'm going to plug in -1, and I get an answer of 4, and that exists. Okay, so we have the first condition has been met. Okay, what about the limit as x approaches -1? Okay, does that exist? Okay, well, first of all, we have defined the left and right hand limits. So we can say, all right, the limit as x approaches -1 from the left, okay, we've already calculated that. That is a 4 because this first function right here is less than -1. That's on the left side of 1. What about the limit as x approaches -1 from the right side? Okay, well, we're going to plug in -1 for the other equation, and you get a positive 4, and that is correct. So therefore, the limit overall is equal to 4, and it meets that criteria. And then finally, does f of -1 equal the limit as x approaches -1? Do the first two values equal each other? Yes, they do. So this is the one example that we have where the function is continuous, and you must write a statement. So we say, therefore, f of x is continuous at x is equal to -1.